Now that we've gone through the detailed operation of a direct map cache, and we've gotten the general idea of the organization of set associative and fully associative caches, we're ready to go into a detailed example. So we're going to compare these different cache organizations for the example that we've already seen when we did a direct map cache. And in that example, we had 16 blocks in the memory, and the cache at any given time could hold 4 of those. So the cache capacity was 4 blocks. And within each of those blocks, we had 4 words, 4 16-bit words. Okay, so let's first look at our address. So our address looks like this. Okay, because we have 4 words per block, then the rightmost 2 bits are the block offset. So those pick one of the 4 when we access the cache. And then the remaining 4 bits that we have here are used to pick one of these 16 memory blocks. Okay? All right, so let's go over first a direct map cache. We've already seen this, so I'm going to go over this kind of quickly. So we have a direct map cache, and we have the valid, the tag, and the data fields. And because we have 4 blocks, then we have 4 sets of these. And we use the index bits, and that's these bits here, bits 3 and 2. And we need 2 of them because we have 4 locations. So we use these index bits to pick one of these 4 locations in the cache. And then we simultaneously read out the valid, the tag, and the data from that selected location, and we bring them out of the cache. We access those out of the cache. And we take the tag field, and we compare that with the tag from the address. Okay. Now the tag from the address is going to be the remaining bits after the index, and that's bits 5 and 4. So we have 2 bits here, bits 5 and 4, and we have 2 bits from the tag, and we compare those. And if those match, and the valid bit is a 1, that says we have a hit. And then we can take the data, we can send it up to the processor, to the selector, and we can pick one of the 4 16-bit quantities to send to the processor. Okay, so that's a direct map cache. Now let's design a 2-way set associative cache using the same capacity of 4 blocks. Now with 2-way set associative, I have 2 places that I can put every cache block. Now that's different than direct mapped, where I have no flexibility. Every memory block has to go in one and only one location. With 2-way set associative, I have the flexibility to put a memory block into one of 2 places. And so what that means is I'm going to have half as many rows, and we call these sets. Each one of these rows is a set. But I'm going to have 2 blocks in each one of those sets. Or we call those 2 ways. It's a 2-way set associative, so we're going to have 2 ways for every set. So let's draw that out. So as before, we have a valid bit. But now we've cut the number of sets in half. I only have 2 of those. And I have a tag, and I have data. But now I have 2 of these. I have 2 ways. I have way 0, and I have way 1. And way 1 will have the exact same thing. I have valid, tag, and data. Okay? So I have the same capacity here. I have 2 blocks here and 2 blocks here, so I still have 4 blocks. I've just arranged the cache differently. So now I need an index, as before, an index bit. And you notice I said bit because I need only 1 now, because I need to pick only one of 2 sets. And so this line here is going to move to the right. So I'm only going to have bit 2 now is my 1 index bit. And then the remaining 3 bits are the tag. So this tag has expanded from 2 bits with direct mapped to 3 bits in each one of these for 2-way set associative. Now I'm going to access this the same way, except I'm going to access both of these ways, way 0 and way 1, at the same time. So I'm going to use the index to pick one of these 2 sets, and then I'm going to read out the information from all of them at the same time. And just as before, I'm going to do a tag comparison. So I'm going to take the tag, and I'm going to send that to a comparator. And I'm going to do that for both of these. Okay, so I'm going to have another comparator over here. Okay, and so I take the tag field from my address, and that's these 3 bits, 5, 4, and 3. And I do this comparison here, and I also do a comparison here. Okay? And just as before, we have to have the valid bit to be set to have a hit. And so we take the valid bit from each of the 2 ways, and we do a comparison. like this. Okay. And so if the data that we want is located over here, then this bit will be a 1. We'll have a hit over here. And if it's located over here, then we'll have a hit here. We'll have this bit be a 1. Now, we're never going to have both of these going to be 1 because we're only going to store the data in one location. Okay? So either we'll have a 1 and a 0 and a 1, or both will be 0. In that case, we haven't found what we wanted in either of the two ways. Okay? So now, in order to determine whether we have a hit, we need to OR these two together. So we send these through an OR gate, and that's our hit signal. Okay, so we read these simultaneously. We do the tag comparison simultaneously with these 3 bits from the address. We find out whether we have a hit over here or neither. And then this signal will tell the processor whether we had a hit in the cache. Okay, so that's the hit detection. Now we also have the data from both ways. And if we have a hit over here, then we're going to use this data and send that up to the processor, actually up to the selector, because we still need to pick one of the 4 words. And if we have a hit over here, then we're going to send this data up to the processor. Okay, so you may have figured this out by now, that I need to add a 2-to-1 mux to pick either this data or this data. So let's do that. So we're going to have a 2-to-1 mux now in our design. And this is going to be the data that comes out of our cache and goes to that selector. All right, so we need to have a select signal here. And because we have a 2-to-1 mux, then we've learned that we need one select signal. Now, if you remember back to a multiplexer, what we do with that select signal is we take it in and we have a true value of it, and we also generate a complemented value. We also put it through an inverter. So we break that up into 2 pieces, its original value and its complement, its inverted value. Because we want to select either this data to go through or this data to go through, depending on whether the select bit is 0 or 1. Now, if you think about it, that's exactly what we have here and here. Okay, so this is like the true and the complement values that we create within our multiplexer normally. So if this is a 1, this is going to be a 0. And then I will select this data to appear out here. And if this is a 0 and this is a 1, then I'm going to select this data. So this is, in effect, our true and complemented values of our selection, our select input to our multiplexer. So we can feed both of these into our multiplexer to indicate that. So we're going to take this value here and feed this into here, this value here, and feed this into here. And so when this is a 1 and this is a 0, we're taking this data and passing that to the processor. And if this is a 0 and this is a 1, then we're going to select this data and send it to the processor. Okay, so this is our 2-way set associative cache. Now the advantage here is that because I have flexibility of where I put data compared to a direct map cache, then I can increase the hit rate. Okay, so a 2-way set associative cache, or a set associative cache in general, will have a higher hit rate than a direct map cache. So that's the real advantage here. The flexibility that I add increases the hit rate. More often I'm going to find what I want in a 2-way set associative cache compared to a direct map cache. But the disadvantage here is that it's not as fast as a direct map cache. Direct map cache is really quick. All I do is I pick these bits, I read them out, and then I'm done. You see we've added some additional logic here in terms of the comparison, in terms of the hit, and also we've added this 2-to-1 multiplexer now for the data. So accessing a 2-way set associative cache takes longer than a direct map cache. So that's kind of the engineering trade-off. We have a fast cache over here, but we're going to have a lower hit rate. We're going to miss more often over here than in this 2-way set associative cache. Okay, and engineers make trade-offs between these two when they're designing a particular cache. Now we can take this flexibility further with a fully associative cache. With a fully associative cache, then I can put a block in any location in the cache. So that flattens this even further. We've gone from 4 sets to 2 sets, and here we're going to have just a single set. So we're going to have a valid bit tag, and data. And we're going to have this 4 times. So again, we have valid, tag, data. I'm kind of running out of room here. Valid, tag, and data. And you may have noticed I've actually drawn this data as not very proportional because this has a lot more bits than what we have in the tag. Okay, but I just made this more compact. So this is our fully associative cache now. So how many index bits do we have? Well, the answer is 0. We have no index bits because we're not selecting any set. We're reading the whole thing out at one time. So now all we have are tag bits. So now we've increased our tag to be 4 bits now. And so what we're going to do is we're going to read all of these out simultaneously. So all of these get read out. All of these get read out at the same time. We're searching the entire cache for our cache block. And so we need to have all of these comparators for each of the tags. And now we've increased the number of comparators to 4. And then we need to have 4 AND gates. So we take our tag and we take our comparator result, our valid bit, and our comparator result. And we do all of these ANDs. And now we need a wider OR gate to collect all of these possible hit signals. And this tells us whether we have a hit. Okay, and again, we're going to have a block in only one of these 4, if any. We could have a miss. And so one of these 4 signals is going to be a 1 and the other is going to be 0. Or they'll be all 0 if we have a miss. So, and now we need to also have a multiplexer for our data. But now it has to be 4-way. Because we have 4 ways now in this case. It's fully associative. So we have 4 locations where our data could reside. So this is our data out. And then remember, we would have 2 select bits, and we'd have true and complemented values of those. So that's like these bits here. So we can feed all of these bits now to our multiplexer. Okay, so these are the select signals that we would have for a 4-to-1 multiplexer. Okay, so the advantage here over two-way set associative is now I have maximum flexibility. I can put a given memory block in any one of these locations. So total flexibility. So I'm going to have a higher hit rate. It's more likely that I'm going to find my data here. If I manage this flexibility, now you may have been thinking about this, you need some way to manage this flexibility. So when I replace a block in the cache and I bring in a new block, I have to choose which block to replace. We don't have time to go over that in this course, but if you go into another course in computer organization, you'll see different replacement algorithms. There's choices if I have all these blocks occupied with data. When I have a new block I want to bring in, I have to choose one of those 4 to replace. So there are different replacement algorithms to try to manage this flexibility in the best way, so I maximize the hit rate. But if I can do that, then I'm going to have a higher hit rate here because I have more flexibility than I had over here. But you see, I've slowed down the cache even more. So the more associativity that I add is if I go to more associativity, here from two-way to fully associative, then I've got more of this logic here. And I've widened now this to a 4-bit, 4-input OR gate, and now I've widened my multiplexer. Those are going to be slower circuits. So this is going to be slower to access, but I have a higher hit rate. So now we have 3 choices, given I have a cache design. I could make a very fast direct map cache, and I'm going to have a lower hit rate, though. I could have this total flexibility over here, where I have the highest hit rate, but it's going to be much slower than a direct map cache. Or I can pick this in-between point, this set associative cache, where I have faster access than fully associative, and better hit rate than direct map. So it kind of forms an in-between point. So what you have really depends on the type of design that you have. So you might have direct mapped or small set associative caches in the pipeline, but other caches, and we'll see in our designs that we have other levels of cache. We may have more wider in terms of set associativity in order to reduce the hit rate.